Welcome back. This is Module 4, and what I'd like to do in this lecture is answer the question, where can I find similar information in commercial instruments? So first a little bit of a review, and then we're going to go over the reports from 4 OCT manufacturers. A disclaimer about these reports. In preparing these lectures, I tried to present current reports that were available, but I want to warn you that software changes occur often, and most manufacturers have many options for the reports. So when I was preparing these lectures in the winter of 2017, I checked with manufacturers to try to get the latest information. But again, to be sure, you'd want to check with the manufacturer of the instrument you have. Okay, having said that, let's turn to a review. So this is our one-page lab report that I spoke about in Module 3. It's based on 3 scans, and it's as I mentioned in Module 3, it's really more a method or a process that's based on 5 principles. And so on commercial reports, you want to look for the aspects associated with these principles. You want to find out whether there's an image that's large enough so you can see details, such as the one up here. You want to check the circumpapillary scan and thickness plot to see if it's an instant, not T-snit. So recall that this is the center of the temporal quadrant when you're plotting something in instant. You want to make sure there's a cube scan that includes the macular and the retinal ganglion cell thickness map. Either one scan that includes both, or 2 separate scans if you're dealing with the 6x6 smaller scans. If you don't do that, you're going to miss glaucomatous damage to the macula. So here's what you'd be looking for. This is macular retinal ganglion cell thickness plot. That's in addition to the traditional disc retinal nerve fiber layer thickness plot. Number 4, ideally there should be probability maps for both the retinal ganglion cell and the retinal nerve fiber layer thickness, because you'll find that it's easier to identify damage typically with probability plots as opposed to thickness plots. So there's the probability plot here on our report for the retinal ganglion cells, and this is the probability report for the retinal nerve fiber layer. And then finally, it'd be nice to have a way to topographically compare the results from visual fields to the results from OCT. So what we do here is superimpose the field points from the 24-2 and 10-2. All right, so that's our report. It's based on 3 scans: a scan of the disc, which is absolutely essential, a scan of the macula, which is absolutely essential, and an optional circle scan of the disc. You can use a derived scan instead. Okay, we routinely get a circle scan, even though it's optional. And we also routinely get a high-definition horizontal scan through the macula to pick up macular damage that is not due to optic nerve or glaucomatous damage. Well, let's start with the Topcon. They have a new report called the 3D Wide Glaucoma Report with visual field test points, or the Hood report. So as you might imagine, I have financial relationship with Topcon. I have equipment grant, and I also have a grant to help support the research. However, I get nothing, not a penny, if you use this report or use their machine. So this is a report that is already in, or will be soon, depending on where you live, available for both the Triton and the Maestro, although it may require ImageNet in order to access it. All right, it's based upon 1 scan protocol, although of course it's always useful to repeat scans. The single scan protocol is 9 by 12 millimeters. So let's just put the fundus view up here and show you the region that's being scanned. So it's 9 by 12 millimeters. It's got 256 B scans. Here's what one of them looks like. And this is fairly high resolution because this is made up of 512 A scans. From this scan here, we can obtain retinal ganglion cell plus interplexiform layer thickness and retinal nerve fiber layer thickness, and then obtain all the information we need for this report from that single scan. All right. The image here is not a circle scan image, it's derived, so it will not be quite as pretty as a high resolution circle scan. But in most cases you can see the details that you need. All right, so as you might imagine, since we helped develop this, the correspondence with our report is quite good. Let's just go through the principles. First of all, an image large enough to see details. Yes, here's the image. It's not, again, quite as pretty as the circle scan, but it will do the job. 2, the retinal nerve fiber layer scan and thickness plots should be shown as N-STIN, not T-SNIT, and the answer is yes again. This is plotted as an N-STIN, and so is this. So this is the midpoint here of the temporal region and temporal quadrant disc, as is this. Excuse me. Number 3, a cube scan that includes the macula and a retinal ganglion cell thickness map. So the cube, in this case, the scan covers both the disc and the macula. So what we do is we take the central 6 by 6 millimeter portion here, and we look at the retinal ganglion cell, and you can see the correspondence. Probability maps are also useful for both the retinal ganglion cell and retinal nerve fiber layer thickness because it's easier to identify damage often. So this is the correspondence to this. And then finally, up here we have the probability plot for the retinal nerve fiber layer. Finally, you want a way to topographically compare visual field and OCT probability maps. That's available here. So this is in field view. That is, it's flipped along the horizontal meridian, turned into a probability plot. And superimposed on this, we have the test locations of both the 24-2, the larger spots, and the 10-2, the smaller spots. And then same here. So that's the Topcon report. So here it is blown up. What you can now do is you can take your, let's say, 24-2, and there are the abnormal points on the 24-2, and you can circle them here. All right. You can do the same thing with the 10-2. We can circle this region here that's abnormal, and that corresponds to that. Right? And that. And you can see the nice correspondence between field and damage and structural damage. It also includes an en face image, which I'll say more about later. You can get an en face images from other manufacturers as well. We included it in the report here. One of the advantages here, it's easier to see the blood vessels and some of the artifacts. So when you see this here, is that a blood vessel or not? Well, it's easier to tell on this that it's a blood vessel. I'll say more in Module 5 about this. All right, so how much information is there in an OCT scan? So here's a validation study we published in 2016. We started with 125 eyes that were either suspects or had early glaucoma. So what made them suspects is they had abnormal or at least anomalous discs. What made them early glaucoma was that the 24-2 was better than -6. So it didn't mean that there wasn't serious defects here, but just using a traditional definition that includes mean deviation, these would be classified as early. To create a reference standard, since there's no gold standard for glaucoma, we had 2 glaucoma specialists who were not involved in the care of these patients. And these two specialists had all the available information we had. They had the OCT reports, they had the 24-2 and 10-2 visual fields, IOP, corneal thickness, history, etc. They agreed on 102 eyes, calling 57 of them glaucomatous and 45 healthy suspects. Now, based only on this wide field report, no information about the fields, no information about IOP, no information about history, I judged 100 of the 102 correctly. That is, correctly being in reference, based on the reference standard. Now, the point here is not, look how good I am. The point here is how much information there is in this report, because this was, I did better than any existing OCT or visual field metric, quadrant thickness, total thickness, mean deviation, pan standard deviation. Right? This suggests that in the future, we'll be able to use artificial intelligence to replace an expert like myself. So here's a study we published last year in which we used just a stock hybrid deep learning model, and it was 93%. Not quite as good as, it didn't do quite as well as I did. It did better than any of the metrics, and we know how to improve it. All right, next, suppose you own the Heidelberg SPECTRALIS machine. And again, financial disclosure, I have a relationship with Heidelberg as well that involves equipment and a small grant. All right, now, what we're making use of in the Heidelberg is the glaucoma module scan protocols. And from a subset of these protocols, we're creating this version of our report. So the actual protocol gives you 11 vertical B scans, it gives you 61 horizontal B scans, and it gives you both radial and circle scans. So this is what we're going to use to create a report similar to our lab report. First, we're going to use the typical circle that has about a diameter of 3.5 millimeters. Okay? And we're going to use this information here from their own report. However, we're going to put it in, and this is TSNIT at the moment, we're going to put it in NSTIN format. And we're going to use the cube scan here that includes both the disc and the fovea or macula. Okay, from this we can get ganglion cell layer thickness, and we can get retinal nerve fiber layer thickness. So here's the draft, which I'm not sure what its final name would be, but the working name is Don Hood Report. So this, let's take a look at this report and then compare it to our 5 principles. First of all, is there an image large enough to see? Yeah, there's an excellent one, because this actually is a circle scan. Actually, the final report will probably have this less black and a bigger image. Second, it's in on our report NSTIM format, so that this is the center of the temporal region, just like in our report. So that's NSTIN. The cube scan here is centered on the fovea, so that we have a nice macular thickness map here, right there, which corresponds to this. We also have retinal nerve fiber layer thickness map, which corresponds to this. We don't have probability plots yet to put here. We will eventually. The initial release, which should be sometime soon, will not have probability maps, but ultimately after FDA approval, these here will be probability maps. For now, they're thickness maps in field view, that is, this is flipped along the horizontal. And we've superimposed on this the 24-2 here and the 10-2 here. So now it's easy to compare field damage to thickness changes. So that corresponds to this, and this will correspond to this, but it's thickness rather than probability. 24-2 locations, 10-2 locations. All right, let me just illustrate the use of a report like this. This is a 46-year-old woman who was referred to us by a very talented neuro-ophthalmologist whose patients we occasionally test. For 5 years, this patient had noted some kind of a gray smear in the upper visual field for her right eye. The referring ophthalmologist wondered about acute macular neuroretinopathy, but read the SPECTRALIS that would account for this defect here, but read this SPECTRALIS OCT as negative, right? Because the pie chart here is all green. This pie chart is all green. The global thickness here is green, all in the normal range, right? So he was wondering what was going on. Right? This is normal, right? Now, does everything look normal to you? We looked at this and we immediately saw why this damage occurred. Because there it is. That little dip there is right where we'd expect damage to be if the macular vulnerability zone was affected. Right there. Now this is T-SNP. So we ran this patient in my lab and we produced this report. Now this is going to be now in instant format. There's the defect, right? There's the thinning in the retinal nerve fiber layer. There's the missing piece. See, this is in the macula. There's the missing piece of the retinal ganglion cell layer in the macula. Here it is flipped in field view with 10-2 points on top. Here's the 24-2 points. We can circle these and circle the thickness map here. You can see the correspondence. Here's a 10-2. We can circle those points and circle this, and you can see the correspondence. If you don't have access to the new report yet, this report here that's standard in the machine, I find particularly valuable. It's T-SNP, so you have to put your own guidance on so that you know what you're looking at. So this spot here is here, and that's in the macula. In fact, it's right in the macular vulnerability zone. You can combine that with the thickness map for the retinal nerve fiber layer and thickness map for the ganglion cell, which you can find in the machine. All right, now, many of you probably, especially in the US, probably use the Zeiss machine. And the common clinical protocols often call for only a cube scan. So many specialists, when they think about OCT and glaucoma, they think about this report here, which is based on a cube scan of the disc. All right. So let's go through our principles. Is there a image, a circumpapillary retinal nerve fiber layer image, large enough to see details? No. Here it is here. It's tiny. You can click on it, actually, and make it bigger. You can see that it's not a great image. That's because it's derived. They could actually improve this by doing what we do, which is to average over an annulus. I bet you this is not averaged over an annulus. But anyway, that image is too small. 2, the circumpapillary scan and thickness plot should be shown as instant, not T-SNP. Do they do that? No. This is still plotted as a T-SNP. Representatives of the company have mentioned to me that they're working on this. I see no evidence that is true yet, but we'll see. 3, a cube scan that includes the macular and the retinal ganglion cell map? No. This does not include the macula. You're going to miss damage if you only have this scan and only have this report. Probability maps, yes for the retinal nerve fiber layer. So this is a nice map and very useful, right? No for the retinal ganglion cell because it doesn't include the macula. A way to topographically compare visual field and OCT probability maps? No. All right. So what should you do if you're using a Zeiss machine? Well, you want to get not only the 6x6 cube scan of the disc that you're used to getting, but you want to get the same 6x6 cube scan centered on the fovea, so it's of the macula. Then you want to use the relatively new PanoMap report, which is available through the Forum software. So again, let's look at this report. Here's a derived circumpapillary thickness plot here, right? T-SNP, unfortunately, right? So this is not based on a circle scan. This is based on the cube scan of the disc. So here's your retinal nerve fiber thickness map. It comes from both of these. And these are probability maps. But they've done something interesting here. This is the probability map for the retinal nerve fiber layer. This is the probability map for the retinal ganglion cell placental plexiform layer. All right, so let's compare it to our report. This is not the same patient, by the way, although the damage is not dissimilar. So that corresponds to that, and that to this. So this is retinal nerve fiber layer thickness, and that's what these two are. This probability map of the macular is the same as this probability map, except that this is in retina view, this is flipped to field view. Field view. So the way to think about this presentation here is it's actually this here combined with this. And again, ours is in N-STIN, this is in T-SNP. I must admit, I find this totally useless, these metrics here. I think they'd be better off just maybe having one or two metrics and then using this space to actually show a nice circle scan. Okay, so let's now go through the principles here. A circumpapillary image large enough to see details? No, but you can see these. You can actually find them in the reports. A T-SNP plot? No, is presented rather than N-STIN, so the N-STIN at the moment is no. A cube scan that includes the macular and retinal ganglion cell thickness? Yes, as long as you get 2 cube scans like for our lab report. Probability maps of ganglion cell and retinal nerve fiber layer thickness? Yes. And a way to topographically compare visual field and OCT probability maps? No, but you could create a way of overlaying this information yourself, such to produce something like this. So here's an example. Here's a patient that we tested that had serious cataracts and had a disc that some of the glaucoma specialists thought was normal, some thought were abnormal. So here's the PanoMap for this patient, right? So there's no standard way in the machine to compare visual field and OCT probability maps, but you could actually overlay the points. So here's what I mean by that. Let's take their report. Let's blow this up, right? And now let's flip it to field view. Let's superimpose the visual field points, which you could do with transparency or something, although once you do this a couple of times, you then don't need it because you have an image of where the points are falling. We now can go to this patient. I think the total deviation here is wrong. I think this is a better representation. That's that point there. To make my point, here's a 10-2. Let's circle those abnormal points, and that's what you get. So you can see the beautiful validation of this. You don't need to repeat the visual fields for this. You know what's happening in this patient based on this, although you may want to repeat the 24-2, in which case I suspect this would clean up. All right, finally, OptiView. I have less experience with OptiView, but from talking to the company and also playing a little bit with the reports, you can get a report such as this one here. This is based on the disc scan. Again, you need, like the Zeiss and like our lab report, you need separate scans of the disc and the macula at the moment. There's no circle scan. Again, it's derived. Here it is, but it's too small, but you can enlarge that. So that's equivalent to that. This is equivalent to this, but again, it's in T-SNP, not N-STIN. So there's a no to principle number 2. This is retinal nerve fiber layer thickness plot. They don't have a ganglion cell, but effectively they have something that's effectively the same, which they call GCC analysis. The GGC is a combined retinal ganglion cell plus interplexiform layer plus retinal nerve fiber layer. So in the macular, it's going to be dominated by the retinal ganglion cells. All right. So here's a thickness map now. So the answer is a cube scan that includes the macula, yes. And a retinal ganglion cell thickness map, yes. That's the thickness map. Probability maps, yes for the GCC. So here's a probability map for the GCC. That's the fovea, right? This is the same patient here. So this corresponds to that. And this corresponds to that. And so this region here is this preserved region here. And here. So that's, as of say December or 2017, that is the best I can do at the moment in terms of trying to help you find similar information in the commercial instrument you might be using. Thank you, and I hope to see you again for Module 5.